We will do another problem from wave equation. A tightly stretched string of length L has its ends fastened at x is equal to 0 and x is equal to L. The midpoint of the string is then taken to a height h and then released from rest in that position. Find the displacement of a point of the string at any time t. So we are given a tightly stressed string of length L. Let the end points of the string be O and B. The midpoint of the string is taken to a height h and then released from rest in that position. So the point A is L by 2h as we are taking the midpoint of the string. So the point A is L by 2h and in that position it is released from rest, means the initial velocity is 0. As the string is divided into two equal parts before it is released from rest, first we will find the equation to OA and equation to AB. We use the 2-point formula to find the equation of OA and AB. We know the formula is y minus y1 by y2 minus y1 is equal to x minus x1 by x2 minus x1. So in the case of finding OA, we can consider 0 0, the O 0 0 as the x1 y1 and BL2H as the x2 y2 respectively. So when we substitute the values, we have y minus 0 by h minus 0 is equal to x minus 0 by L by 2 minus 0, or when you simplify you get y is equal to 2hx by L as the equation of OA, where 0 less than x less than L by 2. X varies from 0 to L by 2 in the case of equation to OA. Similarly, for finding equation of AB, we have y minus 0 by h minus 0 is equal to x minus L by 2 minus L using the 2-point formula. And when you simplify, you get y equal to 2h into L minus x the whole divided by L. In the case 0 L by 2 less than x less than L. So equation to OA is y is equal to 2hx by L when 0 less than x less than L by 2, and in the case of AB we have y equal to 2h into L minus x by L when L by 2 less than x less than L. Now we will find the displacement of the string. We know that the wave equation is dou square y by dou t square is equal to a square into dou square y by dou x square, and a solution to equation 1 is given by y of xt is equal to a cos lambda x plus b sin lambda x into c cos a lambda t plus d sin a lambda t. As we know, the boundary conditions are y of 0t is equal to 0 and y of lt is equal to 0. That means at the end of the string, the end points of the string, the displacement is 0. Now f of x, that is the initial displacement, it is 2hx by L when 0 less than x less than L by 2 and 2h into L minus x by L in the case L by 2 less than x less than L. And since the string is released from rest in the initial point, that means the initial velocity is 0. We have g of x is equal to dou y by dou t at t equal to 0, which is 0. So the initial displacement is given in this function and the initial velocity is 0. Now we will put first boundary condition a into, we get capital A equal to 0. As we have seen, when we substitute the first boundary condition in our solution, we get capital A equal to 0, and therefore the new solution is y of xt is equal to b sin lambda x into c cos a lambda t plus d sin a lambda t. When we put the second boundary condition b in our new solution, we get lambda is equal to n pi by L. lambda is equal to n pi by L. So we have capital A equal to 0 in equation 2 and lambda is equal to n pi by L when we apply the two boundary conditions in equation 2 and in the new equation. So we have y of xt is equal to b sin lambda x into c cos a lambda t plus d sin a lambda t, where lambda is n pi by L. Now our initial condition in D is the initial velocity is 0, that is dou y by dou t at t equal to 0 is 0. Now we have dou y by dou t is equal to, you have to partial derivative with respect to 3. So differentiating 3 with respect to t, we have b sin lambda x into minus a lambda c sin a lambda t plus a lambda d cos a lambda t. Now when you put t equal to 0, dou y by dou t at t equal to 0 is 0 as the initial velocity is 0. We have 0 is equal to b sin lambda x into sin 0 is 0, cos 0 is 1 into a lambda d. So we have 0 is equal to b sin lambda x into a lambda d. The only possibility is d equal to 0. So we can substitute this d equal to 0 in equation 3 and we get y of xt is equal to b sin lambda x into c cos a lambda t, or this is equal to bc sin lambda x into cos a lambda t. We put bc as an and in general we can write y of xt is equal to sigma n equal to 1 to infinity an into sin lambda is n pi x by L into cos a lambda n pi by L into t. Now we have to find the solution to an and you have to substitute in this equation, that will be the displacement function of this particular string. Now to find an, we use the formula 2 by L into integral 0 to L f of x sin lambda x dx, where f of x is 2hx by L in the limit 0 to L by 2 and 2h into L minus x by L in the interval L by 2 to L. So we have to split the integration into two parts and we take the constant outside 2h by L, so that 4h by L square into integral 0 to L by 2 x into sin n by x by L dx plus L by 2 to L L minus x into sin n by x by L dx. We use integration by parts. So that is equal to 4h by L square into first function x into integral of sin is minus cos n pi x by L divided by n pi by L, the constant, minus in derivative of x is 1 into integral of minus cos is minus sin n pi x by L divided by n pi by L the whole square. That is the first part of integration in the limit 0 to L by 2 plus. Now in the second term we have first function is L minus x into integral of sin n pi x by L is minus cos n pi x by L divided by n pi by L minus L minus x derivative is minus 1 into integral of minus cos is again minus sin n pi x by L divided by n pi by L the whole square in the limit L by 2 to L. Now we can apply the limit. So we have 4h by L square into, first we have to put L by 2. So minus L into L by 2 by n pi into cos, when x equal to L by 2 we have cos n pi by 2. Now here you have to put x equal to L by 2 is equal to plus L square by n square pi square into sin n pi by 2. So when we give the upper limit L by 2 we get these two terms. Now we have to put x is equal to 0. So here when x is equal to 0 the first term is 0. When x is equal to 0 we have sin 0 which is 0. So when you apply the lower limit both the terms vanishes. Now you have to give this limit, upper limit L to this. So we have minus, this minus, upper limit L into L minus L. So that is 0. Then here also you have sin n pi. When x is equal to L, you have sin n pi, that is also 0. So when you substitute the upper limit L, these terms becomes 0. So now we have to put the lower limit L by 2. So this minus become plus L into L minus L by 2, that is L by 2 by n pi into cos n pi by 2 plus L square by n square pi square into, when you put x is equal to L by 2, you have sin n pi by 2. So that is equal to 4h by L square into, we can see that this is minus L square by 2n pi cos n pi by 2, and this is plus L square by 2n pi cos n pi by 2. So both will get cancelled, and here it will get doubled, that is 2 L square by n square pi square into sin n pi by 2. Or we can see that this is 8 L square will get cancelled, 8h by n square pi square into sin n pi by 2, which is our required an. When we substitute the value of an in our equation number 5, we get the final solution of the wave equation for this particular problem as y of xt is equal to sigma n is equal to 1 to infinity an. An is 8h by n square pi square into sin n pi by 2 into the remaining terms, that is sin n pi x by L, sin n pi x by L into cos an pi t by L. So this is the displacement function for this particular problem.